Okay, can everybody hear me okay? Yep. So remember that you joined an event called Nerd Nite, okay, just before I start. Hi, I'm just going to introduce myself quickly. So my name's Adam. I'm a software engineer. That's my day job. I was born in Northampton in the UK, and I went to university in Edinburgh, where I then worked for 6 years. And then I moved to Japan in 2014. I've been in Japan since then, so I've been in Japan over half my working career. I used to work for Line, that's one of these pictures, and I'm in my second startup now, so working as a software engineer. And begin plug, I run this website called retirewiki.jp in my spare time, which is a website in English about containing information for people that live in Japan long term, like you guys. So check it out, especially if you have information to add. End plug. Thanks. Okay, so back onto the presentation. So this is a talk about binary and hexadecimal. So binary, it's all ones and zeros, right? And computers use it. That's about what people know. So what I'm going to do is talk about how do we understand binary, okay? Has anybody, is it okay? Has anybody seen this before? Right, this is the Windows crash screen, right? Is it okay? Should I move that way? Okay, this is a Windows crash screen. There's some strange numbers and stuff here, right? This is hexadecimal, so I'm going to talk about hexadecimal as well and what that means. Or if you've ever done HTML or worked with colors, maybe you've seen colors like this with C's and F's and stuff. That's also hexadecimal, okay? So I'm going to explain what that is. But before we do that, we have to go back and talk about what we as humans, how we think about numbers, right? And humans think in tens, okay? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then when we get bigger than 10, our language changes. We start to repeat. So 11 and 12 is an exception in English. But then 13, 14, 15, right? That's like saying 3, 10, 4, 10, 5, 10. Same with 20, 21, 22. In Japanese, it's even more standard because they don't have the exceptions. So juichi, juni, jusan, right? Just tens. We think in tens. Our language is about tens. So does anybody have any idea why our language is based around 10? Hands, right? That's my guess. I don't have any evidence, but it seems to be the obvious. It seems to be the obvious case, right? If we want to do it, we can get 3 and get 5 and add how many fingers we have, or start with 9 and take off 2, and we can count easily. But only as up to 10, and then if you go past 10, you need more hands, or you need to start using feet or something. I don't know. But so that's our language. We think in tens. But same with our writing, right? When we write numbers down, right, we have the number 0, we have the number 1, and using a single digit, we can go up to 9, right? And then we're out, that's it. So with one digit, how many different numbers can we write in English, in numbers? How many numbers are here?
10.
Exactly, right? So our language and our written writing is all about the number 10. Okay, this is where it starts to get a bit technical. Thanks. So I'm going to put a number in a box. So we have the number 1 here, right? And we can write up to the number 9 in a box with a single digit. But when we want to write the next number, we need to do something else. What do we do to write the number higher than 9? Yeah, exactly. So we add another digit, okay? So we start again, right? So there's 10, and we can add 1 to that to get 11, and so on. We can get 42, all the way up to 99. Now we've run out of space again. So what we do is we add another digit and start again, and so on to 1,000, right? We can keep doing that. So say the number 13. What's actually happening here, right? We see a 13, and we just think 13. But there's a process to understanding this number. And what this number 1 here is not the number 1, right? It actually represents 1 times 10. So if we write it out algorithmically, it's 1 times 10 plus 3. Now, this seems like a little bit over the top, right, when it's so intuitive to us. But we're going to talk about computers and automation. And when we start to get into binary, you'll see why this is useful. Same with 42, right? 4 times 10 plus 2. That's what that means. Or if you get to the next number, then that's 100, right? So that's 2 times 100 plus 5 times 10 plus 4. Okay, and the same with 1,000, right? You can keep going. So let me just go back a minute. So there's something happening here, right? Every time we add a new number, we're timesing it by 10 more, if that makes sense. Does that make sense? I don't know. So it's starting to get complicated. So yeah, you can write it like this. So this 10 times 10 could be written as 10 squared. 10 times 10 times 10, 10 to the power 3. You can see a pattern, right? This is the same as 10 to the power 1. 7 is actually the same as 7 times 1, which can, in maths, anything to the power 0 is 1 by definition. So here we go. We've got a pattern. So that number that we wrote before could actually be written like this, which is even more complicated and less intuitive. But the benefit of this is that it's systematic. Now we have 10, and you can see that it's the number times 10 to the power of whatever position in the box is. I don't know if everyone's following, but that's our numbers. That's how we count. That's base 10. That's decimal. That's how Cuba's things. Yeah, I can, but I'm going to run out of time. OK, so this is supposed to be about computers. So why am I talking about all these tens and powers and stuff, right? So if we add numbers together, we can use our hands, as we said. Or if numbers are going to be higher, then we have a system we can use that you learn in school, add it, carry the 1, or you can use a machine, a contraption to help you do that. So, OK, computers. Everyone takes computers for granted, but if we want to make a computer, right, and we want it to calculate things for us, we have to, first of all, be able to represent a number in a machine. We have to have use something in the physical world to represent a number, and then we have to have that calculate stuff for us. And in engineering, at least, you want to try to make things as simple as possible. So if we've got 10 numbers, it's too difficult to work with. So we want to simplify things down. So let's get the lowest number we can possibly think of that still has meaning, right? We could start with 0. That isn't useful. If we've just got nothing, that's no meaning. But if we've got 1, now we've got something we can work with, because you can have 0 or 1. So that's data, right? So there's 2. In one digit now, we can represent 2 values. So can anybody think of something in the real world that has 2 states? It can be 0 or 1 or on and off. Just anything. Light, a light? OK, so that's what I thought of too. Thank you. So a light switch, right? So that has 2 states, right? And then you could have lots of light bulbs together, and that would start to be data, right? Information. And that is what we actually do in computing, right? So if you've, the picture didn't work out because it's dark, but this is a fiber optic cable. So if you've got fiber optic internet, or you've ever used an optical cable for audio.
Christmas trees.
Yeah, OK, but that's not data, but yeah, Christmas tree. Then that's what's happening. It's a little bit more complex than just flashing, and similar for, this is a radio, sorry if you can't see the picture. Similar for Wi-Fi, right? There's a radio wave, and we're modulating it, but it reduces the data down to 2 states, 1 and 0. And same for CDs and DVDs. Like, if you look at a CD in a microscope, it's actually just a little bunch of lumps and bumps and gaps, right? And each bump represents a 1, and each gap represents a 0. I don't know what the technical term is. I call them bumps. And the big one, the game changer, is the transistor. So using electrical components. So transistors and capacitors can be used to make an electronic circuit which has a specific voltage. And then what we say is, if the voltage is higher than a certain amount, that's a 1. And if it's lower, that's a 0. Right? And because we're dealing with electrons here, you can get very small. So now, this is a model of the first transistor. The Apple M1 CPU has 114 billion transistors on it, on the little thing in your chip. Sorry.
How big was the first one?
I don't know, about that big maybe. I don't know exactly. But it was a physical thing. And now it's like billions in a tiny chip, right? OK, so the point is, we've reduced down to 2 states so that we can use the physical world to represent data, right, in an easy way. But if we do that, we have to understand those numbers. So with decimal, we started with 0, and then we went to 1, and we went up to 10. But with binary, that's it. We can only get to 1, right? You can't get up to 9. So how do we work with these binary numbers? Because there's only 2 values, right? So I'm going to go back to the box again. So here, before, we started with 1, and we went to 9, because we're in tens. But in binary, that's it. 1 is the maximum. So this is the number 1 in binary. So how do we write the number 2? Does anybody have any idea? How do we write the next value? Sorry?
1, 0.
1, 0. So add another digit, start again, right? Exactly what we did with decimal, but the maximum is 1. So that's 1, 0. And then you can add 1 to that to get 3. Okay, and then now we're run out of space again. So to get 4, add another digit, start again, and the same again. That's 4, right? You can do the same. That's 8, right? And you can see with decimal it was timesing by 10 every time, but with binary it's timesing by 2. So 4, 8. We can keep going, right? And you've probably seen these numbers before. Like, I don't know, if you ever bought a 256 gigabyte memory stick, or maybe you owned a Nintendo 64, right? That's why these numbers are here, because they're binary, they're powers of 2. That's how the data is physically represented on the disk. So just to quickly say, like, if this is a binary number, not a decimal number, so this is not 11, right? This is binary now. Using the system, this number 1 here now represents 1 times 2 instead of 1 times 10. So writing it out systematically would be like that, 1 times 2 plus 1. So now, before it was intuitive to read this, but now it's not. So this system is useful. And the same again, if you go to the next digit, that's times 4. So 1 times 4 plus 2. So that is the number 6 in binary. And you can keep going, right? So that's 13. Okay, so that's how binary works. And again, you've got the pattern where it's timesing by 2 each time. So you can write it like this, simplify that to 2 times 2. Sorry, I'm going quickly, but the time is short. 2 times 2 times 2 is the same as... So you've got the same pattern that we had in decimal, but the number here is 2 instead of 10, right? So this is the binary number system. So we've done decimal, and this is binary. And this is what we use to understand the physical world of binary. So here's our CD again in a microscope. And let's say there is like some physical bumps here, like a bump, and then a gap, and then a bump, right? That is the bits 1101. And then we can use the system to understand those 4 bumps are the number 13, right? And the same, maybe it's not a CD, maybe it's transistors packed together in a memory chip, but the principle is the same. So that's how we convert these binary digits into a number. Okay, so I've talked about decimal, I've talked about binary, now I'm going to talk about hexadecimal. Okay, so these are all of the numbers that you can represent in binary using 4 digits, 4 bits, from zeros, all zeros, up to all ones. So if we write their values in decimal, that's 0, 1, up to 9, then we run out of decimal numbers, but it goes up to 15, right? So that's 0, this is 15. The problem with binary is it starts to get very long very quickly. Like, you end up with long strings of 0 and 1s, and for engineers, it's difficult to work with that. So we want to simplify it for ourselves. So what you can do is you can write the value. So this is the number 4 in binary, right? This is the number 11. This is the number 3. So you can write them down like that. But if you squish it together, you have a problem, because now we don't know if this is the 11, or maybe this is a 1 and this is 13. We don't know, because we have 2 digits here. So instead of that, computer scientists and mathematicians, probably mathematicians because they do everything, came up with this idea. Well, instead of using 10 here, why wouldn't it be nice if we could write all of these values up to 15 with 1 digit? So instead of 10, let's say A. Let's use letters. So this is 10. Right? And then it goes up to F, which is 15. So F is 15, which represents this binary value. And then if we write it, instead of 10, instead of 11, we write B. Now if we write it like that, it's not ambiguous. It's clear. This is 4, this is 11, this is 3, right? It's maps easily. So that's hexadecimal. And the reason hexadecimal is useful is because we can store 16 different values in 1 digit in hexadecimal, which is the same as the number of values you can store in 4 bits in binary. So it maps quite well. And you can see it mathematically as well, because 2 to the power 4 is 16, but OK. And that doesn't work for decimal, because 10 is not a power of 2, right? So binary and hexadecimal work well as good friends together, basically. OK, so I've talked about decimal. I've talked about binary. I've talked about hexadecimal. And the presentation is called Bits and Bytes, but I haven't talked about bytes. So now I'm going to talk about bytes. So a byte in computing is defined as 8 bits. There are 8 bits, so 8 digits, 8 binary digits in 1 byte. So that's just the definition. There's history behind that, and it's to do with encoding alphabets and stuff, but I'm not going to go into it. So if you've got 8 bits, the minimum value you can represent is 0, right? And the maximum is all 1s. And we know that 1 hexadecimal digit represents 4 binary bits, So to represent 1 byte in hexadecimal, you need 2 characters. So if you write a byte in hexadecimal, the minimum is 0 and the maximum is FF, which is the maximum of hexadecimal, which is 255 in decimal. So I don't know if I'm losing people now, but it's the same. If you do the maths here, you can do the same thing we did before, where F is the value 15. So you can do 15 times 16, and you can do 15 times 1, which is 240 plus 15, which is 255. So it works out the same. So this FF is the same as value as this series of 1s, which is the same value as 255. Back to the HTML colors. So before, what are these C's and F's for? Well, now we know that 2 hexadecimal values is 1 byte, right? So we can see this color here is represented as 3 bytes on a computer. It takes 3 bytes to store 1 color. And computer monitors, like this projector, issue 3 different kinds of light, right? Red, green, and blue. So each color is represented with 1 byte. And because there's 8 bits in a byte, it's not decimal, then the maximum value is 255. So this is like an even number divided by 16, basically. So this represents 100% green, and then quite a lot of red, and a little bit less of blue, and that mixed together gets you that value. So that's what we use hexadecimal for in numbers. Okay, quick recap. I'm already 16 minutes. So humans count in tens, which is called decimal. Computers count in twos, which is called binary. We use 16s, or hexadecimal, to make writing binary shorter for ourselves. Each digit in a number represents a base raised to a power. So what that means is this number is not necessarily 100. It depends on the system you use, right? So if we treat this as a binary number, this 2 here represents 2 to the power 2, which means 4. Or if we treat it as a hexadecimal number, this 1 means 16 to the power 2, which means this actually is 256. So that's how base works. And finally, then, we know that 2 hexadecimal digits means 8 binary bits, which represents 1 byte. Okay, and then finally, this whole discussion about computers and numbers has been based on the fact that we reduce everything down to zeros and ones, like two states. But if you think of the light switch, you can have a dimmer switch, right, that changes to unlimited number of states in one light. So if we think of the abacus, like instead of 2 states, you could choose 10 different ones. Then the amount of data we can store in the same physical space is now 5 times more, right? Or you could say, okay, instead of 10, I want to do 50. But it's hard to make something that does that. But if we could make it, then the potential for future computing is, everything is now based on 2, so the potential is unlimited from here on, right? If we improve the engineering. Okay, that's the end. Thanks for listening. Yeah, in my.
Thank you, Adam. Okay, we got a little bit of time for Q&A.
Should I keep?
So, yeah, please stand there.
It was 25 minutes when I practiced, so sorry for speaking too quickly.
Yeah, so we got a little bit. We do have enough time then for some lots of questions. So please hound him, please.
Question, sorry. Sega Master System or Nintendo Entertainment System? Which one? Those are 8-bit systems.
Yeah, well, that was before my time. So
Okay, fair enough.
In the UK, we had the Sega Mega Drive, which I think was also different. Genesis, yeah.
In America's marketed.
I think that was 16 bits, right?
Yeah, 16 bits. That was a 16-bit
and
system.
PlayStation, which was 32.
32, yeah.
Could you explain what it means when you say it's an 8-bit console?
No. Well, the processor processes numbers in blocks of 8.
Okay.
That's what that means. So 1 byte, right? And if 16 bits, then it's processing 16 bits of information at a time. It does the calculation. And now we're at, what is it now? 64 bits?
Well, they don't even count anymore.
Now processors are 64 bits.
Oh, they're 64.
Yeah.
Okay.
But the Nintendo 64,
That's
anyway,
quite old.
Yeah. Doesn't that mean the Nintendo 64 was the most powerful?
It might be, but it wasn't. I don't know how the name for Nintendo.
I have a question. It's very easy to understand this way when you talk about integers. But if you talk about something very finite,
Fractions.
yeah, fraction is very difficult
yes.
to understand. Yeah, intuitively.
Okay, so yeah, well, the way fractions work in computing is, yeah, this is just an integer, like you said, that's a number, we translate to number. But a fraction is much more complicated.
Yeah.
So we define a system that says, okay, these numbers are going to represent the base, and this is getting like, yeah, we represent, how can I describe it? You need a system, and it gets much more complex.
Yeah.
And floating point numbers is difficult.
That goes to negative as well, right?
Yeah, negative numbers as well. So I only talked about positive numbers here. So in computers, like what we do actually to represent a negative number is say if it starts with a 1, that's negative. That's one way. So this I said is represents the value 255, but in most computers actually that's the value minus 128, and there's a system for that as well. Yeah. Usually what you do is, if you want to know the details, is that if that's a 1, then you invert the rest of the numbers after that to get the binary value. It's called 2's complement in mathematics. I don't know if you know. Yeah.
I was also thinking, I mean, it's very one-dimensional, right? You go from 0 to 1, one state to another.
Yes.
But in life, most things are multidimensional. So
Exactly. So where was the last slide? I lost it. Yeah, I don't know. Anyway,
you're going back.
I'm going backwards. The switch, yeah, so we reduce it down to 2 states deliberately to make the engineering easy. But where's the end? I don't know. Yeah, like the dimmer switch, right? There's an unlimited number of states, so we just cut it to 2 because that makes it easier to design things for, basically. Thanks a lot.
No more questions?
He's starting to point out the flaws.
I have a question ahead of
sure.
it. So we talked about, I don't know how much this question is going to be referring to this, but I hear a lot about quantum computing recently.
Yeah.
Is that the dimmer switch, or there's this infinite potential about that?
Yeah, I don't know. I can't explain quantum computing to you, but I don't know how quantum computing works actually, but for example, it means that you can have multiple states at the same time, I think, with quantum computing, which means that, so the premise of cryptography, which is using using difficult mathematical problems to make things difficult to solve. With cryptography, when you know the answer, it's easy, but if nobody tells you the answer, it's hard. That's how cryptography works with prime numbers. But with quantum computing, that blows it out of the water. You can't do it anymore. So, yeah, or it's something. Yeah. Sorry, I don't know.
So you just mentioned prime numbers.
Yeah.
So you have other series of numbers like prime. You've got Fibonacci series. Is that any relevant in this kind of?
There's no difference between binary and decimal and hexadecimal when you're talking about numbers, because the value is the same. It's just how we write it down. So this is the value 255, right? It takes 8 ones, but this is 2 to the power of 8 plus 2 to the power of 7 plus 2 to the power of 6, which is the same number. So a prime number written in binary and decimal are exactly the same.
So basically, we shouldn't care about prime numbers. So prime numbers, Fibonacci series, from an engineering perspective, they don't matter?
They have properties, right? Mathematical properties, but in numbers, they're just numbers.
No.
Right? It has the property that it can't be divided, but that's it.
Sorry, is that a question?
No, I mean, like, I have a lot going. The thing is, what I'm basically understanding, this is less about numbers themselves in the way that we humans understand them, as much as it is ways of representing numbers so that they're easier to process in terms of one state or another. So basically, by packing more information into one digit, we can say more with one representation of that.
The final point.
Yeah. So that's the key, because it's easy for the computer to understand one thing, because it doesn't have intuition in a sense, so that it can actually process. Okay, there's a difference gradation between 1 through 10, which is something that requires immediate intuition of what numbers
Yeah.
are relative to
We have to design a machine that can understand it, right? So we have to design a machine that can understand numbers. So we've got, like, most things are transistors and capacitors, right? Electrical circuits that work in zeros and ones. So
Yeah.
making something that can understand more than those two states is very difficult. So that's why everything is binary.
But ultimately, everything is going to come down in the way we currently understand computers to simplified versions of those two states in some way or another, at least so far as we understand now. Like a lot of this is, like for example, hexadecimal is a way of re-representing ultimately binary combinations.
Yeah, hexadecimal is just a way of representing a binary number in a shorter way. So that's just the way we represent it.
Exactly.
But binary is we're using binary to make computers because it's easier to engineer.
That's right, exactly.
Basically. But then we use hexadecimal so we can write them down in a shorter way.
It's interesting.
There's also representations of numbers that you can't do in a universal way, like Roman numerals, for example.
Yes, yeah.
You can't create a systematic way of counting.
I deliberately didn't talk about Roman numerals. Because I said humans write in tens, but Roman numerals don't, right? You've got 1, you've got 5, and all sorts of things. So, minus, prefixes. And, Sure.
So talk how like binaries represent numbers. How do they end up like representing alphabets, like ABC?
Yeah, similar to the fractions.
Yeah.
So we just design a system. So you'll have this. So in 4 bits you can store, what was it? 2 to the power 4. So 16 different numbers, no more than that. Anyway, so this is a number. But for alphabets, what we do is just design a translation that says, okay, the number 13 is the letter A. I think it's 26, I'm not sure. Do you know what A is? Anyway, so just define, this number is A, this number is B, this number is F, and it goes, and you do the same for the $sign, right? And then you have this encoding. And then the problem is there's multiple different ways of doing that. So if you ever had the problem with the yen and the backslash, that's because there's 2 different encodings that have the same number in binary. So depending which system is looking at that number, it reads it a different way.
Well, that explains a lot.
Yeah. I was going to put that in, but it's too long already.
Probably one more question. All right, if that's all I got, then give another round of applause. All right.